All right, so in the last part of this character table derivation, we're just going to finish up figuring out these three remaining irreducible representations. And so the way we're going to do this is we're going to use cubic functions. And these transform as the f orbitals. You don't really need to know what the f orbitals functions are. They can be tricky to memorize, but the key point here is that we just want to derive new functions, and the best way to do that is by multiplying by z. So just if you remember in an earlier video in this series, what we did is we multiplied z times xy, and that x comma y, and that gets us xz comma yz. So by multiplying gamma 2 by gamma 9, we got gamma 10. Now we're just going to do that with the quadratics that we derive. So we're going to derive an irreducible representation by multiplying gamma 2 by gamma 4 and also gamma 2 by gamma 5. So let's do, to start out, we'll do gamma 2 by gamma 4. That's going to give us the cubic function x, y, z. Let's see if that gives us something unique. So we do 1 times 1, gamma 2 to gamma 4. 1 times 1 is 1. So we already have a 1 written down there. Then we're going to have 1 times negative 1 is negative 1. 1 times 1 is 1. Negative 1 times negative 1 is 1. You can see so far we're tracking the same thing as gamma 5. We're not unique yet. Z, get negative 1 here times negative 1 is 1. Now we're different. Actually, this is unique. Let's see. But I tracked that wrong. Negative 1 times 1 is negative 1. We're not unique yet. Negative 1 times 1 is negative 1. Now we're unique. So this is a new function. Negative 1 times negative 1 is 1. And then we have negative 1 times 1 is negative 1. And 1 times negative 1 is negative 1. And 1 times negative 1. 1 times 1, sorry, is 1. So in the end, we end up with this new function. I'm just checking that I got this right here, because you can get lost in the table because there's 100 characters in this character table. That is right. So we got x, y, z. Next one, we're going to do gamma 2 times by xy. And that's gamma 2 times by gamma 5, which gives us another cubic function, which is z times x squared minus y squared. Or you can factor that out and call it zx squared minus zy squared. Either way is fine. And so again, we go 1 times 1 is 1. We already have that. 1 times negative 1 is negative 1. 1 times 1 is 1. Negative 1 times 1 is negative 1. Next one is negative 1 times 1 is negative 1. Sorry, negative 1 times negative 1 is 1. Now we're under inversion here. Negative 1 times negative 1. Negative 1 times 1 is negative 1. Negative 1 times negative 1 is positive 1. Negative 1 times 1 is negative 1. 1 times negative 1 is negative 1, and 1 times 1 is 1. And let's see, did we screw that up there? We did. This is 1 times 1. We're timesing by gamma 6 there. And this is supposed to be a negative 1. And if you look at this, it's a unique function. So that's gamma 7. Easy way to come up with these cubic functions. We didn't have to derive themselves. The very last, gamma 8 is what we have to do. Gamma 8, it turns out, doesn't derive as any cubic function or any linear or quadratic. There's other functions, probably way more complicated, that aren't really chemically relevant, that it could transform as. And so the thing at this point is just to look for patterns, and we're trying to figure out what this is, not using a function, but using some other character table rules. The best character table rule to use here is the orthogonality principle. The orthogonality principle tells you that when adjusted for the dot products, it will be equal to 0 of any two functions, and that dot product is adjusted for the number of symmetry operations in each class. So as an example, for example, gamma 1 is let's just do an example of the dot product. Gamma 1 dotted with gamma 9. Any of these permutations, any of these dot products have to be equal to 0. But this again is adjusted for the number of symmetry operations in each class. So the way to write this is, well, gamma 1 is 1, 1, 1, 1. We have 10 ones, right? 6, 7, 8, 9, 10. And then the number of symmetry operations in each class, let's not worry about that yet. We have to multiply by gamma 9 to components. So multiply by 2, by 0, by -2, by 0, by 0. I'm just going here, by -2, by 0, by 2, by 0, by 0. And then we add all these up, but we have to multiply by the number of symmetry operations in each class, okay? So we have one identity, we have two C4s, so that's times by 2. We have one C2, we have two C2s primes, we have two C2 double primes, we have one inversion, we have two S4s, we have one sigma H, and we have two sigma V's and two sigma D's. Now looking at this, the zeros go away. So all these zeros go away, and we get a value here of 2, 1 times 2 times 1. We get a value here of -2, 1 times 1 times -2. We get a value up here of -2, 1 times 1 times -2. We get a value up here 2. So we end up getting 2 plus -2 plus -2 plus 2 is equal to 0. So we just proved that gamma 1 dotted with gamma 9, the orthogonal, the dot product equals 0. So I'm just showing you how that works. But we're going to use that idea to figure out what gamma 8 would have to be, okay? And what's nice about the gamma 1, using gamma 1 as an example, is 1s across the board, so it didn't do anything. And if you look at any of these other gammas that are one-dimensional, okay, you can think about how many -1s there has to be. And so you have to have, when you're normalizing for this, you have to have, remember there's 16 operations in this point group. So 8 of those operations are going to have to be positive ones, and 8 of those are going to have to be negative ones in order to get you equal to 0 for being gamma 1, right? Because gamma 1 is all positive ones. So how can you split this up? So you can see, like, one way that's split up is that you have in gamma 2, you have 5 -1s and 5 positive ones. And so that's a logical way to split it up. How is that split up? Is 5 went to 8, 5 went to the other 8, right? The -1s are 2, 2, 1, 2, and 1. That equals 8. And then the positive ones were 1, 2, 2, and plus 2 plus 2. That's also equal to 8. So is there another way to break this up? You can look for other cases where there's 5 -1s. Here we only have 4 -1s, right? In gamma 3, but they were with 8 again, 2 and 2 and 2 and 2. Here we have 5 -1s. So it's a 2, a 2, a 2, this is gamma 4. So we're going to have 4 -1s and a 2. So we have 4 2s. Has to be that way. Here we have 4 -1s. They're all under 2s. Here, gamma 6, we have 5 -1s, another 5 -1s. It's a 2, a 2, a 1, and a 1 and a 2. So that's how you have to do it. 2, a 2, 1, and a 1 and a 2. So 3 2s and 2 1s. Okay, here we have, so we're just looking for patterns. Again, we have 5 -1s here. And again, we have 2 2s, 3 2s, sorry, and 2 under -1s. So we have, this is under a 2, under a 2, under a 2, and then these 2 are under 1. Now, another way, you stare at this for long enough, very simple way, very symmetric way to do this is to just have -1s at the end. 5 -1s just at the end. And if you do that, look, you got 1, 1, a second 1, those are your 2 1s, and then you got 3 2s. 1, 2, 3. That works. And we are forced to have a 1 here, and so then we know we need to have 5 positive ones. So that's going to be orthogonal with gamma 1. We could check it with something else, right? Like with gamma 9, you're going to get a 2, positive 2 here. This is a 0, so it goes out. Get a negative 2 here. Those cancel each other out, the positive 2 and the negative 2. Then we have a positive 2 here, and we got a negative 2 here. Cancels each other out. Again, those are all under 1s, so I didn't have to worry about that. But anyway, this takes some just guess and check and some pattern recognition here. It's sort of like a big Sudoku puzzle at that point, but there's only one that we had to do this way. So hopefully that's not too hard. The other 9 irreducible representations we're able to figure out with the functions. You could have Sudoku'd almost the entire table out using the orthogonality principle, but I like using the functions because it's a lot more straightforward. So the very last thing to do is just rename these things with their Mulliken symbols, because now we know what the irreducible representations are. So the way that we do this is we look at the dimensionality, which is the number underneath the dimension, underneath the identity operation. So in this first column here, with the way that we oriented things, and if we have a value of 2, we call it an E, okay? And later on, in a bit, we'll have to differentiate between these 2 E's, but both of these are going to be E's, and they're going to have subscripts, but we'll worry about that in a second. And then if you have a dimensionality of 1, okay, you're going to call it an A or a B. And you're going to give an A if you're symmetric with the principal rotation axis. And you're going to give a B if you're anti-symmetric with the principal rotation axis. The principal rotation axis, remember, talked about way in part 1 of the video, is C4. And so if you have a value of 1, symmetric, you're going to give it an A. So this is going to be an A, and then we also have an A, so 4 A's, and then we're going to have 4 B's. These are anti-symmetric ones. B, 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 and B. And then we're going to give them G's or U's, whether or not depending on whether or not they're symmetric with the inversion operation. When you have an inversion operation, G stands for Garada, means symmetric. So the ones are all going to get, under I, are going to get G's. So this is going to be a G. This is going to get a, sorry, that's not going to get a G because it was a negative 1. Let's erase that there. This one, though, is going to be a G. This one's going to be a G. The next 2 B's are going to be G's. Okay, and then we have negative 1s and negative 1s. So for the negative 1s, you're going to use U. Oh, sorry, an E. We have a positive 2 here, so we call this EG. For the negative 1s, we're going to use, or negative 2s, we're going to use U. So we have negative 2 here, that's going to call it EU. EU and EG, they're differentiated. We're done with those. This has a negative 1 under inversion, so it's a U, negative 1, a negative 1 there, it's a U. And this A up here had a negative 1, so it's a U. But we have to differentiate between the different AGs, because we have 2 AGs, the different AUs, we have 2 AUs, the different BGs, and the different BUs. The way we do that is we add 1s and 2s as subscripts moving forward. And we're going to look at the C2s. Now, which C2 do you use? Do you use C2 prime or C2 double prime? Perpendicular C2s. That's the way you do it. It's hard to know. These Mulliken symbols aren't perfect. There is some ambiguity to it, but people always do it in a certain way. And so the way that they end up doing it here is with respect to the C2 prime. And I'm even having to look at this because again, this is not any sort of science. It's arbitrary here. And so I'm just double checking, and yeah, it's with respect to the C2 prime. So we have here we're symmetric. C2 prime we have a 1, so we give it a 1. If we're anti-symmetric, we're going to give it a 2. So this is going to be a 2. And then we have A2G here because we're negative 1 under C2 prime. We, under X, for the XY function, that we had a negative 1 there, so that's going to be a B2G, that's our B2G. This is going to be our B1G because we had a positive one here for x squared minus y squared. And then we have B1U. That's our x, y, z. And we're going to have a B2U. That was our one. That was z times x squared minus y squared. Our very last one here is going to be an A1U because we're symmetric with respect to that. That was the one that we didn't have a function. We had to Sudoku them. So there you go. There's the entire derive D4h character table. We derived all 100 characters, looked at a lot of the cubic functions, all the quadratic functions, all the linear functions, a rotation function even. You can check this with something that you'd find online, but we derived almost all of this and definitely all 100 characters, and we got the Mulliken symbols. We got all the classes and the operations, of course.